In this lecture, we will make an introduction to a very powerful method to formulate a dynamic circuit of arbitrary order. Okay, and it's called obtaining the state equation. Okay, so we will give a rough definition of state equation, which will become more and more precise as we go along through certain examples. And then after a while, once we're familiar with obtaining that formulation, we will discuss about obtaining the solution once we have the formulation. Okay. So for many benefits, especially from the computational and theoretical point of view, engineers and physicists and lately even biologists, because system science has made a very important entrance to that field also, usually formulate a given LTI system, which, by the way, can easily be generalized to the nonlinear systems too. Okay, so that's something we should keep in mind. But for a while, we'll be concentrating on the LTI case only. In terms of the so-called state equation. It has the following form for an LTI system: x equals x being a vector, some matrix times x plus some other matrix times our other variable, also a vector, w. Okay, where x is a vector, say in Rn, and this number here, n, is said to be the order of the system. W also a variable, a vector, let's say of order n, size n. So that means we have n individual inputs. This represents the input vector. So they are therefore functions of time. As for A and B, they are constant matrices, where the entries of those matrices are determined by the system, or for our case, by the circuit parameters. Okay, A in n by n, so A is necessarily a square matrix, and B is n by n matrix. Okay, once again, n is the order of the system, and n is the number of individual scalar inputs that we have in the system, where x is the state vector, but sometimes we just drop the word vector and just call it state. Okay, let's call it state vector. W is the input vector, or in short, it's simply input, and matrices A and B are fixed. Okay, they're constant matrices. Okay. Now let's see on a very simple topology how this equation emerges. Okay, and then, well, that simple example will give us a rough idea what is meant by a state, and what's A matrix, what's B matrix, what's W, and so on. Later on, we will try to develop systematic approaches to obtain this equation, state equation, for a given circuit. Okay, our example is a circuit we're already familiar with, a topology we're already familiar with from 201. Okay? A series RLC circuit. Which we already know, formulate, and solve. But this time we will try to formulate it in a way that we haven't before, namely through the state equation. So this is our input for this system or for this circuit. This LTI, so we have R, L, and C as our system, our circuit parameters. This is the direction of the inductor current, and this is the polarity of the capacitor voltage. Okay. So we know, obtain a solution, let's say by solution we mean capacitor voltage. For that we need two things besides the parameters. We need initial conditions, namely initial inductor current and initial capacitor voltage, plus we require the input voltage waveform. Okay. Now, so we know how to model that. We have a way to model that. We can write a second order differential equation, LTI, in terms of capacitor voltage, or in terms of inductor current, or in terms of, let's say, the resistor voltage. Okay. And then we know how to go from there, having written that formulation. But let's try to formulate the circuit this time through this type of equation. Okay. So for that, what we do is, let's write down certain terminal equations. What we know is CdVC equals IC. Okay, and IC equals I, because there's only a single current in the circuit. So let's write it down, I. And from this equation, we can write dVC or VC dot. Note that this notation dot means derivative with respect to time. dVC equals 1/C times I. Let's call it R equation 1. Eventually it will be R equation that describes our first state variable. Okay. How about the terminal equation for the inductor? For that, let's write down KVL. We know that R IL plus this voltage, which is R times IL, plus this voltage, which is VL, and in terms of IL, it's L times VIL. And finally, plus the voltage of the capacitor, okay, by KVL equals the voltage supplied by our input, Vs. And from that equation, which we obtain using KVL plus the terminal equation for the inductor, let's obtain DIL. Okay. DIL equals minus 1/L VC minus R/L IL plus 1/L Vs. Let's call this equation 2. Okay. Now let X, which will be our state vector for this example, be VC and IL. Okay, so that's vector in R2, two-dimensional space, and entries are capacitor voltage and inductor current. So if we choose this as our state, okay, by the way, we haven't yet defined what we mean precisely by state, but that's going to happen later. Suppose that this we choose as our state. Note that I use the verb choose. That means for a given system, the state choice is not unique. So this be our state, and in this case, for this simple circuit, the input is just Vs. Okay? So in this case, it's a scalar. But in the general case, we may have more than one input variables. An independent voltage source here, an independent current source somewhere else, and so on. So in general, the input will be a vector. But in this simple example, it's only a scalar, which also is a vector of size 1. Okay. Then, combining 1 and 2, we can obtain our state equation, having chosen the state as VCIL. Then equations 1 and 2 imply the following state equation. X dot equals A, X plus B, W, and W in this case is simply Vs. Okay. This is our A matrix in state equation, and this is our E matrix. Okay. X is this vector VCIL because that's how we chose it. X dot is simply VC dot and IL dot. Remember this notation. Dot notation means derivative with respect to time. So let's therefore fill in the entries of these matrices. Here we have 4 entries to figure out, and here we have 2 entries to figure out. So that makes a total of 6 numbers. Okay. So let's start from the first row. For that, we look at the first state equation. First state is VC, so we have to look at the VC dot equation. VC dot is here, dVC or VC dot equals 1 over C times IL. Okay, so therefore, VC dot equals 0 times VC plus 1 over C times IL. And finally, how about input? Input does not directly appear in this equation, therefore 0 times Vs. Okay? So that the first equation, therefore, gives us the first rows. How about the second row? We look at the second equation. IL dot equals minus 1 over L Vc. Okay, so that's that entry. Minus R over L IL. So it goes here, minus R over L IL. And how about Vs? Plus 1 over L Vs. Okay, therefore here we have 1 over L. Okay, so this is therefore the state equation for this circuit or for this system for the choice of state VC IL. Okay. Now let's try to be a little bit more precise about certain words that we have used. For instance, the word state. Okay, this is an important question. What is state? Okay. For a given circuit or for a given system. Now here is an answer. It's a minimal. Okay, so by minimal we want to be as economic as possible. Set of data is set to be the state of a system. And for our case, we're talking about circuits or networks. If the following conditions are satisfied. Here is the first condition. If we know x t0, let's say, through, let's say, measurement, you know the initial state, initial value of the state vector, and the input waveform, or input vector waveform, for all future times, okay, from t0 to infinity, and usually with laws of generality we can take t0 to be 0 because we're dealing with LTI circuits, at least for the beginning. We can determine evolution of the state, or sometimes called the solution of the system, for all future times. Okay. So that's one thing. And for an input-free system, so that would mean if you know the initial conditions, you should be able to, if that's a proper state choice, you should be able to figure out all the future values of the state variables. And the second condition to be satisfied is the following. If we know x of t for all t and input w of t for all t, then we can compute any voltage or current. We can call this the output of the circuit. Let's call it y of t in the network. So this value of y at that particular time t must depend only on the time, on the values of x and w at that particular time t. Okay. Therefore, if you know x and w, you should be able to automatically figure out y without solving any differential equation or any. Okay. You solve the differential equation to obtain x of t, but once x of t is known, plus the input is known, then everything should be automatically known. Okay, so that has to do with the definition of state. Now, here is a remark regarding the non-uniqueness of the state. Let's put that in mind. The choice of the state for a given circuit or a system in general is not unique. When possible, and most of the time it is possible, we will be using the natural choice, by which we mean capacitor voltages and inductor currents. For mechanical systems, usually natural choices, the positions and velocities of certain links, let's say. To the natural choice, namely capacitor voltages or sometimes charges stored in capacitors and inductor currents. Or sometimes magnetic flux associated to the coils. Okay, so that's what we mean by the natural choice. Now, in our simple example, the series RLC circuit, it was easy to obtain the state equation, okay, because the topology was very primitive. But when you have a slightly more complicated network, then obtaining the state equation may not be straightforward. And in order to develop a systematic approach, what we need is we need certain tools, some help from graph theory. Okay? So therefore what we're going to do now is we're going to briefly remember some of the useful concepts useful to the state equation formulation from graph theory. Okay. So under that remark, we will begin our very short review. Graph theory is a useful tool or a field that contains many useful tools, okay, in obtaining the state equation in a systematic fashion. So that's the motivation for our review. So let's start remembering with what a tree was, or a given graph. Given a connected graph, and graph is basically nodes connected by certain edges, okay? Given a connected graph called G, a tree of that graph, T, is a subgraph that contains all the nodes G, and a certain selection, which is not unique, of its edges, such that it contains no loops, but still is connected. Contains no loops and is still connected. Okay. Let's see some very simple examples. So that we'll have a nice understanding of a tree visually. Example. Suppose that this is our graph. Okay, which has 1, 2, 3, 4, 5, 6 nodes. Nodes are represented by dots. And then edges or branches or sometimes arcs, they are all represented by those lines segments. So suppose that this is our graph G. Okay. For our purpose, we don't have to label nodes and edges at this point. So whatever our tree is, it must contain all of these 6 nodes, and it will contain some of the edges such that it will be connected but contains no loops. For instance, this make a tree. Okay, let's call it T1. It contains all the nodes, it's connected, okay, clearly, and there are many loops within T1, so that's a tree. Another tree is this. You have this edge, this edge, this edge, this edge, and this edge or branch. Okay, so that's another tree. Let's call it T2. It contains all the nodes. Clearly, it's connected. Okay, for any node you can go to, you can reach any other node, and it doesn't contain any loops. Therefore, that's also true. Let's see some non-trees for the same graph. Okay, this is, for instance, also a tree, but if you also include this edge, this is no longer a tree. Although it's connected and contains all the nodes, it's not a tree because here we have a loop, and loop is a closed path. So not a tree because it's containing a loop. What else? These 2 edges and these 2 edges are chosen. Now for this graph, this thing, this whole thing, considered as a single entity, is a subgraph, okay? Because it contains a subset of nodes and subset of edges. But that subset is not, or a subgraph is not a tree, because clearly it has 2 components, meaning that it's unconnected. Okay. Here we have one piece, here we have another piece, and if you're going to go from a node that belongs to this piece to another node to this other piece, then you cannot find a path that connects those 2 nodes. Therefore, due to unconnectedness, that subgraph is not a tree. Because it's not connected. Okay, so it's quite clear what we mean by a tree. It's quite a visual definition. So let's move on to what remains once you pick a tree, which is called Cotree. Okay, and then using tree and Cotree, we will be defining fundamental cutset and fundamental loops, and defining those concepts, fundamental cutsets and fundamental loops, will be very useful when writing KCL and KVL equations. And writing those equations will be useful in obtaining eventually the state equation. Okay. Having remembered what a tree was, now let's move on to this concept of Cotree. Given a graph and a tree associated to it, all the remaining branches form associated. Okay, associated to the given tree. Associated Cotree. Okay. Here is what we mean. This time, let's label the edges. Okay. This is our graph, the original graph, the same topology here. This is our G, and here, this is how the branches are labeled. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So this is a 6-node and 9-edge graph. Now, to indicate our tree selection, we're going to darken the branches that belong to our tree. Okay? So suppose that we work with that tree. So that means this branch belongs to our tree, this branch number 4, belongs to our tree, and so on. And finally, branch number 7. Okay. So these are thick branches indicate tree branches, and the normal branches, remaining branches are branches of the so-called Cotree associated to this tree. Okay. So T1 is the set of branches 1, 4, 8, 9, and 7. And then the associated Cotree is whatever remains branch-wise, which is 2, 3, 5, and 6. The edges here plus the edges here, they make the total edges of the initial graph. This is Cotree of the given tree T. Okay, now having defined tree and Cotree, or having remembered tree and Cotree, we're now ready to review Cutset and loop. What loop is clear. In fact, we already used that definition here. So let's therefore concentrate on Cutset. Here is what Cutset was given. The connected graph let's call it graph G. A Cutset is a set of branches of G with the following properties. There are two properties to be satisfied simultaneously. First of which is removal of all the branches of the Cutset makes the graph, or leaves the graph unconnected. The graph G. Okay, so that's the first condition. The second condition is a condition that prevents, or that ensures prevents redundancy. Okay, after removal of all the branches, accept an arbitrary one, the graph G has to remain connected. Okay, still stays connected. Okay, but what is meant by those two conditions? Let's try to understand on some visual cases after defining fundamental cutset and fundamental loop. For instance, this 1 and 2 is a cutset of the graph G. Why? Because if you remove all the branches of the cutset, okay, if you remove 1 and 2, then okay, the graph becomes unconnected. Here we have a node and here we have the other piece. So from this node to other piece, you cannot go by a path. Therefore, the graph is unconnected. If you remove all the cutsets except one, in this case it's very simple. We have two branches. That is, if you remove one and leave two, then clearly the graph is connected. If you do this other, if you remove two and leave one, the graph still remains connected. Therefore, this set that contains branch number 1 and branch number 2 is a cutset, for instance. Now we're going to talk about those cutsets and loops that are called fundamental. Now, the definition is a bit long, but once we see applied to an example, it will become quite clear. Okay, what it is. So let G be a connected graph. It's always our starting point. Okay, and for that graph, T be a tree. And finally, C is the associated Cotree. Okay. We have a graph connected. For that, we choose a tree, or perhaps we're given a tree, and then once we have the tree, we automatically also have the Cotree. Given a branch, let's call it B1, that belongs to our tree T1. We can, excuse me, belongs to T. We can construct a cutset, it turns out. The first of the branches in our cutset, let it be B1, okay, the branch that we pick from the tree, and then the other branches are called B2, B3, and so on, up to Bk. K is the number of branches in our cutset, where all the complementary branches, okay, that is all the branches except or other than B1. B1 is our first branch. B2 up to Bk belong to C, okay? So we're given a graph and a tree. From that tree, we choose, or we're given a branch B1, and then using that branch we construct a cutset. Okay, respecting the following constraint, that cutset contains our branch B1 and also contains other branches, but those other branches must necessarily belong to cutset C. Okay, excuse me, Cotree C. This cutset, it turns out, can always be picked. Moreover, it's unique. Okay. This cutset is unique, and because of its uniqueness, it's called a fundamental cutset associated to branch B1, which is coming from tree T. And it is called the fundamental cutset associated with branch B1, which is coming from our tree. Okay. We will have some examples, but before that, let's also dispense with the dual definition, the definition of the fundamental loop. Then we will see some examples, and finally we will emphasize their use in obtaining the state equation. Fundamental loop. Okay, dual of fundamental cuts. Now, this time we start with a branch from the Cotree. Given a branch, let's call it B1 tilde, that belongs to Cotree C, we can construct a loop. A loop is a closed path. B1 tilde, B2 tilde, B, let's call L tilde, where all the complementary branches, okay, by which we mean branches except B1 tilde, B2 tilde, now to BL tilde, belong to the tree T. Okay. It turns out that such a loop can always be found. Moreover, it's unique. That's why it will be called fundamental loop. This loop is unique, and that's why we call it fundamental. We call it the fundamental loop. Associated with the Cotree branch B1 tilde. Okay. Now let's see some example. Let's use the same graph. the labeling is as before: 1, 2, 3, 4, 5, 6, 7, 8, 9. The tree branches are darkened or thicker. Okay, 1, 4, 8, 9, and also let's pick 6. Okay, it's connected, contains all the nodes, and it contains no loops. The tree. Okay, so our tree is, and suppose that it's given, is 1, 4, 8, 9, and 6. 1, 4, 8, 6, and 9. This immediately determines the Cotree. Cotree simply is whatever remains, namely 2, 3, 5, and 7. Two, 3, 5, and 7. Okay. Now, according to our definitions, each of these tree branches, they set a fundamental cut set, and likewise each of these Cotree branches, they determine a fundamental loop. So let's figure out, by looking at the graph, those fundamental cut sets and fundamental loops. Okay, fundamental cut sets. Okay, according to our definition, each tree branch determines fundamental cut set 6 and 9. Okay, let's figure those out. For the one, first of all, it must contain one, that tree branch, and it must not, all the other branches must come from Cotree. Okay, it's not difficult to see that. This is the cut set, that is namely 1 and 2, that's associated to tree branch 1. Okay, so 1 and 2 is fundamental cut set associated to tree branch 1. Note that, for instance, 1, 3, 6, and 7, they also make a cut set. That cut set also contains the branch 1, but that cut set doesn't satisfy the constraint that all the remaining branches come from the Cotree, because in that cut set 1, 3, 6, and 7, we also have 6. 6 is a tree branch which is not allowed. The only tree branch that's allowed is 1, for the fundamental cut set associated to tree branch 1. Now, with this 4, we have this. Okay, 4, 5, 3, and 2. Okay, 4 cut set associated to this guy. 8 is this. Okay, 8, 5, 3, and 2. And so, for 6 is 6, 2, 3, 7, and finally for 9 we have 9 and 7. Okay, so that's quite easy. Let's also figure out the fundamental loops. Each Cotree branch must define a fundamental loop, and the Cotree branches are 2, 3, 5, 7. So we're talking about 4 fundamental loops. 2, 3, 5, and 7. And the first branch must be the branch of the Cotree. Okay. With Cotree 2, we're talking about a loop that contains branch number 2, and also all the other branches must come from the tree. And it's easy to see, it's the loop that we're talking about is 2, 6, 8, 4, and 1. 2 belongs to Cotree, and all the remaining branches come from the tree. 6, 8, 4, and 1. 6, 8, 4, and 1. Then, as for Cotree branch 3, we have this 3. Note that 3, 2, 1 makes a loop, but that's not a fundamental loop because it contains 2 Cotree branches, 3 and 2. But we need only one Cotree branch, and it's 3. So there's only one choice, and that's 3, 6, 8, and 4. Okay. So this thing that makes a loop is our fundamental loop. 3, 6, 8, and 4. And with 5 we have 5, 8, and 4, and finally for 7 we have 7, 6, 9. Those are our fundamental loops. Okay. Now, having defined fundamental cutsets and fundamental loops, now we're ready to use them in our state equation obtaining procedure. Okay. Here is a procedure to obtain state equation. Okay. Namely, first we have to choose the proper state, and then we have to obtain the state equation. Okay. So this is our step 1. Choose a tree that is proper. Okay. And by proper tree selection, we mean the following. A proper tree satisfies the following. All the independent voltage sources are in the tree. Okay, so that's one part, constraints. And all independent current sources must be left outside. In other words, they must be in the Cotree. Okay. Then, if there is an ideal transformer in our circuit, one and only one of its branches must be included in the tree, and all the remaining ones must be in the Cotree. One and only one of its branches is in the tree. And by tree we mean our proper tree. And what else? Maximum number of capacitors, or the branches that are representing capacitor, must be in the tree. Capacitors are in the tree. And the dual condition also holds. Maximum number of inductors must be in the Cotree. Are in the Cotree. Okay, Okay, so that's what we mean by a proper tree. So having chosen our tree will help us in two things. First, we will be able to properly choose a state vector, and then having chosen our state vector, again using our tree, or more precisely speaking, using fundamental loops and fundamental cutsets, we will be able to write the individual state equations. So step 2 is choose a state vector composed capacitor voltages and inductor currents. But those capacitor voltages and inductor currents must be such that the capacitor voltages must belong to capacitors that belong to the proper tree, and the dual case holds for the inductors. Okay, voltages in the tree and inductor currents in the Cotree. So that's our step 2, state choice. Then in step 3 and step 4, and to get perhaps it may be also suitable to consider them as a single step, or step 3a and step 3b, what we do is we write down these state equations. Okay? So for each fundamental cutset, defined by capacitor in the tree or in our proper tree. Write KCL equation, like the current equation. And step 4 or step 3b is the dual of this step. For each fundamental loop defined by an inductor in the Cotree, write KVL equation. For each fundamental loop defined by an inductor in the Cotree, write KVL equation. So let's end this lecture by clarifying what we mean by writing KCL and KVL using fundamental cutset and fundamental loop respectively. Again, let's use our favorite graph. One, two, three, 4, 5, 6, 7, 8, 9. Okay, so this was our tree. Now, since we're talking about KCL and KVL, we also need some directions. So let the directions be given, or we choose it as follows. 5, 6, 7, 8, 9. Okay. We have the labeling, we have the direction, we have the tree selection, and automatically we also have the Cotree selection. Suppose that this tree, whatever our circuit is a proper tree. Okay. For the fundamental cutset, fundamental cutset defined by the tree branch 8, which is 8, 5, 3, and 2. 8, 5, 3, and 2. Let's write down the KCL equation. By KCL, we have the following. Okay. Now, this cutset is, let's show it like that. Okay. And then this we can consider as if it's a closed surface, and therefore by KCL we know that the currents entering a closed surface must equal the currents leaving, the sum of currents leaving the closed surface. Now we have this 8, suppose it's entering into our closed surface, and suppose everything else is also doing the same thing what 8 does, that is entering. So that means all the currents are entering, and then sum of all those currents must equal to 0. So let's write that down. This is I8. Okay. And then here we have another current that's entering. I5 is in that direction, therefore entering current is minus I5, so minus I5 is entering. Then we have 3 plus I3 entering, and finally we have I2 entering. Okay. And that equals by KCL to 0. So that's what we mean by writing KCL equation using the fundamental cutset. Okay. Let's also talk about the dual operation, writing KVL at a fundamental loop. For the fundamental loop, okay, defined by Cotree branch 2. So it's 2, 6, 8, 4, and 1. 2, 6, 8, 4, and 1. Okay. By KVL, we have, now we're talking about the voltages. Suppose that the direction of the loop is determined by the direction of the Cotree branch, which is 2. So what we have is this voltage plus this voltage plus this voltage plus that voltage, finally plus that voltage equals 0 by KVL. So starting from V2, okay, V2 plus this voltage, which is, since this is V6 plus minus this voltage is minus V6, minus V8, minus V4, and plus V1 equals 0.